Alright, so we're going to tackle 3.4 and 3.5. Both are very different, honestly, from kind of what we were doing in the other sections of Chapter 3. And 3.5 is honestly just completely different, but here we go. So, just like in Chapter 2, we learned how to solve linear equations. Then, we learned how to solve linear inequalities. Now, those were basic linear equations and inequalities, so they were only in one variable. But hey, we just spent 3.1 through 3.3 dealing with true linear equations and graphing lines. Now it's time to graph linear inequalities, as you can see below. So, the first thing we need to know is we need to just learn this one other thing about inequalities, is that these two will be dashed lines. And these two will be solid lines. Alright, so in other words, if you have the or equal to, you'll have a solid line. You'll fill in all those gaps because you can be equal to. If you don't have the or equal to, you cannot actually be on that line, but that line is the boundary, so we dash it. Alright, from there, what we need to know is if it says y is greater than blah, 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 that means above for your shading. And if it says y is less than or equal to, right, it could be greater than or equal to or less than or equal to, whatever that algebra is, we shade below. All right, above and below is what you always want to think. There is one special case, and we'll see that here on 3 and 4. But here we go. So the good news is a lot of this, you've done the heavy lifting, and so this section should go by fairly quickly as soon as you grasp shading. So look at number 1. It's got a y-intercept at 1, 2, 3. It's got a slope of down 2, right 5. I could also go up 2, left 5. And usually what I would do is I would then draw my solid line and move on. But wait a minute. I now stop and go, wait, do I draw a solid line or do I draw a dashed line? Well, this doesn't have the or equal to, so I'm going to draw a dashed line. Now, you won't be drawing by hand. You'll be using your online tool, and maybe we'll show you an example of that. But there's my dashed line. Now, it then says y is less than, so that's this scenario here. It doesn't matter about or equal to or not, but it's got the less than, so I should be shading below my line. Now, what that means is, take any point on this graph and move below or move down. So that would be down here. This would be down here. And if I even start to do that, that's my shading, but we'll draw it like that. Now you'll see in your online homework, all you need to do is drop one little paint bucket, either on this top section or this bottom section, and it takes care of the rest. But that would go ahead and be my line for this one. Maybe let's do the other ones in pen, but hopefully I don't mess up. Up next, I've got a y-intercept at -1. I've got a slope of up 1, 2, 3, right 1, 2, 3, 4. I could also go down 1, 2, 3, and left 1, 2, 3, 4. And this time it's or equal to, so that's solid line. And it says y's can be greater than my line, right? That's the other way of saying it, is I want y values greater than the line you graphed. Well, here's the line I graphed. Where are y values, vertical values, greater? Well, the greater values are up above, so I'm shading in this area. Drop your paint bucket anywhere here, and you're done. So, again, if you really took to heart 3.1 and 3.2 and got through those homeworks, this should really be a breeze by comparison because you've done the heavy lifting of learning how to graph a line. Now, up next, I'm going to have to do, one in pencil, one in pen, because I kind of forgot that the shading is going to mean two different things. But honestly, this will be kind of a tease of Chapter 4. We've got two equations here. I'll do this one in pen. This one says the y values can be less than or equal to -3. Now, these are your special lines. These are your horizontal or vertical lines. let's take a look at these. If you remember my little phrase, it's the variable you see is the axis you cross. So for this first line, I see y, so I'm going to cross through y at -3. And if I'm crossing through y at -3, that's going to be a horizontal line. And it can be a solid line because of the or equal to. Now from there it says I want the y values less than or equal to. So if y values are less than what I graphed, they would be below. I'm going to do that kind of lightly because I'm not sure what the next example is going to hold. But up next it says x can be greater than 5. So I'm going to cross through x at 5. That's right here. And I'm going to cross through, but I'm not going to cross through as a solid line. I'm going to cross through as a dashed line. Again, hopefully we can kind of see that that's a different color. From there, if I'm greater than, now this is the one thing, usually we say we shade above and below, but this is a special case because there is no above or below because it's, a vertical line. Maybe that's another reason we call this undefined, because the regular rules don't quite apply here, do they? So it's left or right in this case. In this one special case, when it's a vertical line that you need to shade. Well, if x values can be greater than a value, if I'm on the x-axis and I'm wondering where's greater, that's to the right. So here I am shading that side of the right-hand line. All right, so there you go. You got your, again, horizontal line. We'll make that a little bolder just so we can see the difference. And then I've got my other one. Now, again, what I'm saying is this is a little bit of a preview of Chapter 4, because Chapter 4 will actually be graphing 2 at the same time, and we'll start asking where do the both shaded regions overlap, which will be right here for this problem, but again, that's Chapter 4. I just wanted to save a little bit of space and keep this all on one page. We've got one more example, and believe it or not, we're already done with 3.4. This is a little bit of shorter of a section because, again, you've already done the heavy lifting, so to speak. You already learned the concepts of graphing through the other 3. You're just applying the, hey, am I drawing it with a dashed line or a solid line? And am I shading below or above, or in that one special case to the left or the right? So this one is, again, just a little bit of an algebra stretch because you're not yet ready to graph this line yet. What you should do is you should get this into slope-intercept form, even though there's an inequality, and then graph. So to do that, I would subtract the 5x first. I would then divide by -3. But whoa, when I divide by a negative, remember that the inequality flips direction. Super interesting there. That still happens even when we're, in a later chapter graphing x's and y's. As long as you divide it by a negative, you need to switch that inequality. All right, -5 over -3 is +5 over 3. And +6 over -3 is -2. There's my slope-intercept form. From there, my y-intercept then would be -2. My slope would be up 1, 2, 3, 4, 5, and right 1, 2, 3. I could also go down 1, 2, 3, 4, 5, and left 1, 2, 3. Still fits the same pattern. This is going to be a solid line because it has the or equal to. And I want the y values below my line, so if I just put my pencil on the line and think below, that'd be going down. So anywhere over here would be where I could drop that paint bucket, so to speak. All right, now I was going to pull up the graphing tool and just do a little bit of the 3.4 work with you, but I'll just upload that as a separate video because I was having a little trouble pulling it up while I was uploading the other videos that I did this evening. Anywho, so just look out for that. There will be kind of a video guide for using that graphing tool to graph 3.4 inequalities. Anyways, let's finish up 3.5. Again, this one's going to be pretty different. Here we go. What is a function? A function, I guess I would say this. uses the same methodology or algorithm such that each time an input is repeated, the output is the same. All right, and to use a little silly illustration here, a lot of us have been to McDonald's, and so the thing about McDonald's is you can go into the drive-thru and you can order a number 1 or you can order a 4A, the spicy chicken sandwich. Or no, I think it's 4C. Anyways, you can order, a 1, a 4C, a 5A, and you should get the same thing every time because, well, if not, you would say McDonald's isn't functioning properly. You should be able to say 4A and get your McCrispy chicken sandwich every time or whatever the menu item is. And if you don't get it the same time every time, then things are not functioning properly. Somewhere there was a mistake made. That's the idea, is you should have the same output every time you use the same input. Now what that also means, or maybe what it doesn't mean in reverse, is you can get different outputs for different inputs. You can also get, now this is where that analogy kind of breaks down, you can actually get the same output for different inputs in the mathematical sense. So sometimes, and this isn't too surprising, but we can plug in 2 into a function and get 4. We can plug in -2 into a function and get 4. Just to use some notation early on to get that around our heads. What would that function be? It'd be x squared. Right? If I plug in +2 into this, +2 squared is 4. If I plug -2 into this, -2 squared, careful, that's -2 times -2, it's still 4. So as long as your input is unique, that input is always going to give you the same output you got any other time. If I say, or even just as a class, right? If we're all functioning as a class, if I say, what do I get when I plug in -2, and we all don't agree, then some part of our class isn't functioning properly. We should all have the same answer for this question. All right. Some more kind of basic vocab is domain. This would be the input, what we plug in. Sometimes we would just call that the x values. All right. And so that would mean the range is the output or the y values. Now, there's one more kind of test here. And we can say, rather, am I a function? And here's what you ask yourself. You ask yourself 2 questions. 1, does x repeat? Because, and this kind of sounds silly, but based on my definition, if x never repeats, we'll never know if, we'll never know what I should have gotten or whatever. We're just going to assume based on the very vague things we have here, right? We've got, hey, you plugged 1 into something and got 5. I have no idea what I plugged it into or why. I plugged 2 into something and got -3. So I don't know what I'm doing here, but somehow 1's turning into 5, 2's turning into -3, 3's turning into 1. And so we're getting all these different things, but when we're looking at it in this sense, in the more mathematical sense, less how can I make it real life, if your x value never repeats, then you're a function. So if no, you just found a function. And then if yes, then you move on to step 2, and you say, did you, I don't know I'm saying you, but did it produce, or did you get the same y value. And notice this time, if the answer is yes, you're a function because you need to get the same result, right? The whole class has to answer the same number. Every McDonald's should give you the same item when you order 4A. And if the answer is no, I guess, well then you're done. It's not a function. So this is kind of the most important part. If you memorize this, it's a really easy way to determine a function. And we'll look also at, again, the graphical sense. Maybe you looked ahead. But here we go. Does an x value repeat? Well, I've got a 1, a 2, a 3, a 4, and a 0. Guess what? This is a function. Because no x value was ever repeated, so I'll never know if things aren't functioning properly and they don't agree every time. It's a function. Up next, I've got a -1, a 5, a 4, a -1, and a 3. Now notice again, I'm only looking at the x values first, and I'm noticing now, wait a minute, I've got some repeated x values. So -1 was repeated, but produced different outputs. Guess what? Not a function. All right. Different ways of displaying the data, but that's fine. Take a look at these x values, -2, -1, 0, 1, 2. That's a function because the x value is never repeated. And then up next, 12, -1, 6, 2, and 6. Wait a minute. Those just repeated. And gosh, now I'm thinking 6, 2, 6 and Lilo and Stitch. But oh well. Anyways, this would not be a function. And again, it's not because 6 is repeated, but it's because 6 produced 7 and 12. Now, if this below, right, if this said 6, 7, and then below it said 6, 7, this would be a function. Or if they both said 6, 12, and 6, 12, it would be a function because the x value repeating doesn't mean it's immediately not a function, right? If the x value repeats, it means go to question 2, and then you get your yes or no. So it's okay to have your x value repeat. It's just in all the examples we had here on the page, when the x value repeated, a different y value came out, so we didn't have a function. All right. Other things to say, and I kind of said this before, right? In fact, if you didn't know, this one is, at least at this point, x squared, just to throw that out there. And this is that example of, hey, look, it doesn't matter that the y value was coming out multiple times, you know, the 4 and 4 and 1 and 1. It just matters that if the x values repeat, we get the same y value every time. All right. Of course, there's a graphical way of dealing with this. So there's such a thing as, sorry, it got cut off, but the vertical line test. If you're a function, it means any vertical line, and watch this wording, passes through the graph, and careful again on this wording, at most once. At most. It doesn't have to touch the graph ever at a certain point. It just cannot touch it twice. We'll say at least one vertical line passes through twice. All right, let's look at these examples. If I'm drawing a vertical line over here, well, it touches nowhere. That's not a problem. If it touches here, it touches once, but if it touches here, it touches twice. Again, that's just an example. We could put a line here. We could put a line here. There's all these vertical lines that pass through more than once. Now this next one looks a little tricky because this looks like it's getting pretty vertical pretty quick, but trust me, this is a function. Any vertical line you graph passes through only once. I mean, even look at that, grid on the axis. I know it's small, but it technically, this graph doesn't back up and double back, so to speak. It keeps on slowly moving to the right, even though it's moving vertically very quickly. Here, again, we've got issues all over the place. There's a bunch of vertical lines that pass through more than once, so no. All right. The very last section here, really quick, is just plugging stuff in via function notation. And this is hopefully pretty easy. It's just substitution again. So we start writing functions as f of x. We won't see this too much in the course. It's more so just an introduction to what college algebra will show us. But f of x, has an x, and then they replace that with a 3. Well, then guess what you do? You replace with a 3. Everywhere there's an x. Notice that I'm writing my parentheses for good substitution. And now I just follow PEMDAS. I use parentheses. Well, any parentheses is already simplified. I use my exponents. First time we've done that in this course. Now I do my multiplications, which would be 36 and negative 6. There's still a 3. And now I do some combining, and it looks like I would end up with 33. Honestly, for sake of time, I'm going to trust that you could go through that section, and I think I just want to look at the graphical interpretation of this really quick. And we can actually connect a lot of dots here because, again, this used to say h of x. And so let's look at it this way. This means that x is 1. And we've learned how to graph x is 1. X is 1 will cross through the x-axis at 1. There's that vertical line from the vertical line test. So I'm looking at the vertical line, x equals 1, and I'm saying, where do I cross? And look, I cross at negative 3. So what is h of 1? H of 1, where this graph is when I have a vertical line crossing through 1 on the x-axis, is down here at negative 3. From there, it gets pretty easy. Well, what about when I'm at 0? Well, here's the vertical line at 0. Where are you on the graph? Over here at negative 4. What about at negative 2? At negative 2, here I am. I'm at 0. And there we go. That's all of 3.5, and we've now finished Chapter 3. Awesome. I look forward to going through Chapter 4 with you all soon.